Assalamualaikum and a very good day, class. Now let us move into chapter 2, 2.1.2, the solubility limit. In the previous chapter, we have learned about all the terminology in the solid solution, which is solute, atom or element with lower amount, solvent, element with higher amount, solution, combination of solute and solvent, and we also learned about solubility and the solubility limit. We also learned about the solid solution type. Solid solution type, we have two types, which is interstitial, where an atom with smaller radius enter the area within the bigger atom, and substitutional solid solution, where it must comply 4 rules. The first rule is it must comply to atomic radius, the same crystal structure, the same electronegativity, and same electron valence. Now, in this subchapter, we shall learn about the solubility limit. Let us take a look at this first example of phase diagram. A phase diagram is actually a diagram that shows the transformation of phases. Let's say from liquid to solid, or from liquid to liquid plus solid to solid. This example is a water-sugar system. In this phase diagram, it shows the solubility limit of a sugar in water. Solubility limit is the maximum concentration for which only a solution can occur. Okay, so this line over here is the line of solubility limit. Over here, we know that this is a liquid solution or syrup, and over here is the liquid plus solid, which is the solid sugar. And we know with the increment of the temperature, it will increase the solubility limit. If you apply a heat, okay, to a material, okay, of course, okay, it will increase, okay, the amount of material to be added to the solution. So if I ask you, what is the solubility limit of sugar to water at temperature of 20 degrees C? So what you do is you drag, okay, the line over here until it reach the solubility limit line, and you drag it downward, and you shall see that at temperature of 20 degrees C, the composition for sugar that can be added is 65 weight percentage. WT stand for weight percentage. Okay, 0 over here is pure water, meaning to say we have 100% pure water, and this one 100% pure sugar. 100% pure sugar meaning to say 0% pure water. 0% pure sugar meaning to say 100% pure water. Okay, I hope you understand, okay, the concept of solubility limit. Now, let us answer this question. If the composition of sugar is more than 65%, what is the solution that occurs? So look at this one. Okay, at 20 degrees C, if it is more than 65, the phase that can occur is liquid plus solid. Okay, and if it is, sorry, this one is less than 65. Less than 65 is what can occur is syrup, okay, or liquid solution. And if the composition is more than 65%, what can occur is, what phases that can occur is syrup plus sugar or liquid plus solid. And as I've mentioned before, the solubility limit increases with the temperature. Solidification is the most important phase transformation because most metal and alloy will undergo this transformation before it becoming useful object. All metal are heated and melted before it can form into any useful object or product. And solidification will involve liquid solid phase transformation. For example, casting process. The solidification process different with others because some metal are pure element, some metal are alloy element. Let us take a look at how solidification occurs in metal and alloy. First, they will form a stable nuclei in the melt. We call it as nucleation. And number two is the growth of nuclei into the crystal. And number three, the formation of grain structure. So first we have the liquid, okay, liquid metal or liquid alloy, and then they have the nucleus. And then the nucleus, okay, as the temperature reduces or decreases, okay, the nucleus will grow. Okay, it will grow bigger and bigger and bigger until it touch each other and it will form a grain boundaries between the crystal. So this is how solidification occurs from liquid to solid in metal and alloy. Okay, from a solution, which is the liquid state, to nucleation of crystal, to crystal growth, and lastly, the crystal will grow together and form a grain boundaries. Now we move on to the cooling curve. We all know that when the temperature rise, it will become liquid. When the temperature reduces, it become solid. So of course, it involves a cooling curve. Okay, the cooling curve is used to determine the phase transition of the temperature. The temperature and time data will be recorded and plotted. Okay, and the produced graph, we know it as phase diagram. It shows the relationship between temperature, composition, and phases present in alloy. So let us look at this phase diagram or cooling curve. Okay, the first one is the pouring temperature. It is the highest temperature that the material or the liquid can attain. Okay, for example, the pouring temperature for an aluminium is 660 degrees C. So when it reach that temperature, it become liquid and it can be poured. Dia boleh dituang, okay, into the mold. Okay, so that one is A. Okay, it is actually a liquid state. So, and then it will reduce until it reach B point where it start to freeze. Okay, it start to become solid. And then from this part, okay, the crystal will grow and grow and grow until it reach the point C where it cannot uh, expand anymore and it will form a boundary between each other. And that one is where the solidification end. And lastly, okay, all of the grain, okay, the atom grain shall have certain time to cool. Okay, certain time to cool. So from C to D is the cooling of the solid. Okay. There are differences between the cooling curve of pure metal and the cooling curve of alloy. Pure metal, meaning to say the element have 100% the same material. For example, 100% aluminium, 100% ferrum. You do not add anything into the material. It is 100%. Okay. Pure metal solidify at a constant temperature, meaning to say, okay, the time where the freezing begin and freezing complete is the same. Okay, it does not reduces, it does not decreases, it is the same, it is a straight line because there is no different material inside. They only one material, they take their own sweet time to freeze. Okay, so this is how it looks like. Still have the same pouring time. Okay, and then still have the liquid cooling time, and the freezing begin over here. The same the same temperature, okay, until the freezing is complete. Then it goes down to the solid cooling. Okay, so here is the, from the pouring time to the freezing complete is the total solidification time, and from the freezing begin to the freezing complete is the local solidification time. So the cooling of your metal, the freezing begin and freezing complete is a straight line. But if you have an alloy, what happened? Okay, if you have an alloy, it will not have the same freezing begin and freezing complete time. Okay, so most alloy will freeze over some temperature ranges because metal A have some let's say metal A are added, the freezing temperature is 800. The metal B, when when we combine with metal B, the freezing temperature is 400. So 800 and 400 are two different melting temperature. So when you combine together, you have to find a point where they're met together. Okay. So the difference between alloy is the freezing is at the the freezing begin and freezing complete is not the same, so it is slightly decreased. So as you can see here, over here, okay, on top of the freezing begins, it is actually liquid. Okay, on top at the bottom of freezing complete it is actually solid, and in between at the freezing begin and freezing complete it is a combination of liquid plus solid. Okay, this one is when you add nickel and copper together. So at 50% nickel and 50% copper, okay, as you can see, okay, here, okay, there are combination of 50% copper and 50% nickel. There are some solid and some liquid occurs. Okay, look at this temperature. These are the melting temperature for nickel, and these are the melting temperature for copper. Different melting temperature. So you have to find something in between to know at what point does the nickel transform to liquid solid, and what point does the copper transform to solid. So this is the point lah. You know that this two is the time where freezing begin and freezing complete. Okay, and after you know that after this temperature, both can occur as a solid solution. Okay. Now let us take a look at this video.
When we pour the molten metal in the mold cavity, we see that the solidification process starts from the sides of the mold, then moves towards the molten metal. This is because the sides of the mold provide sufficient cooling to the molten metal. After some time, we see that the molten metal solidifies in the form of randomly oriented crystals. The region where the crystals are formed acts as the production area and is called the nucleus. When the molten metal solidifies further, we see that the shape of the crystals changes to long columnar crystals. Having their axis perpendicular to the sides of the mold. Thus, the shape of the molten metal crystals formed will be as shown. Note that during solidification of metals, the temperature remains constant. This can be represented graphically as Now let's discuss the solidification of alloys. When we pour the molten alloy in the mold, we see that the solidification process takes place in the same manner as in case of solidification of metals. The only difference is that the crystals formed will have a dendritic structure as shown. Note that during solidification of alloys, the transition from liquid to solid state occurs during the change in temperature. This can be represented graphically as
So generally, that is how solidification occurs in metal and alloy. Development of a phase diagram. So as you can see, series of cooling curve can be occurs at different metal composition, and the point of change of each slope of cooling curve will construct the phase diagram. For example, if you have pure copper over here, okay, we know that the temperature for the pure copper to become solid is actually from A to B. But when you add 20% nickel, okay, the freezing time begins and the freezing time end have actually changed. So here are liquid 1 and solid 1. But when you add 50% nickel, we have liquid 2 turn to solid 2, and 80% nickel, liquid 3 turn to solid 3, and lastly from pure nickel, C is the same as D. So when you plot the graph, you will have this as your phase diagram. Okay, I hope all of you understand there's a transformation from liquid to solid, and in between liquid plus solid. Okay, we have solid alpha, solid beta, and many more. Okay, this is the cooling curve for binary isomorphous material. For pure metal, the cooling curve will show horizontal thermal arrest at the freeze point as seen from A to B over here. Okay, and we know that different composition will give different cooling curve as from liquid turn to solid at phase 1, composition 1, and liquid turn to solid at composition 2, and until it reach 100% solid at the end. Okay, so the slope changes at L1 up to L9, okay, or up to the liquid point over here before the freezing point from C to D. We call it as liquidus point or liquidus line. And the slope solid, okay, from B up to this point, we call it as solidus point. Okay, and we also know that up above the area of liquidus line is actually red region, the material is liquid, and the green region, the material is a combination of liquid plus solid, and lastly at blue region, the material is solid. Okay, by removing all the excess, you can get, okay, the phase diagram for certain material or alloy. So I hope that all of you understand how to construct the phase diagram of both metal and alloy. Okay class, that's all for today. Thank you so much for your attention.